The first one will be about chemical strengthening of glass. And the presentation will be done by Guglielmo Macrelli, who is a true glass scientist. He has served as the R&D responsible, chief scientist, and then finally as the chief technology officer at Isoclima in Italy. And he has been doing his whole career around chemical strengthening of glass, publishing more than 50 articles around the years, speaking all over the world in different conferences and events. So, Guglielmo, floor is yours.
Thank you, Ricky, for the nice presentation. Ladies and gentlemen, good afternoon. Today, the topic I will speak about is chemical strengthening of silicate glass by ion exchange. And I will focus more on the role of alkali nitrate salts, which is normally not so considered in this type of technology. This study has been performed together with my colleague Elisabetta Poli of Isoclima, and together with a company in Spain, Quality Chemicals. Obviously, they are manufacturing alkali nitrate salts, and that's why we got a collaboration with them. Let me start with an outline. First of all, we will speak about the relevance of chemically strengthened glass by ion exchange. We will shortly call it IX in terms of products and applications. Second, we will start a little bit of discussion about ion exchange for chemical strengthening in terms of theory and mathematical model. I will keep the discussion at a little bit simpler level, even, but not too much simple. Okay. Next point would be the alkali nitrate salt, namely we will concentrate today to potassium nitrate in terms of industrial production of this chemical and how you can characterize this for ion exchange applications. Then we will discuss a little bit about the experimental methods we have followed for the qualification of this type of chemicals for our applications. And we will finally present some result of a comparison with different types of industrial potassium nitrate salts, and hopefully some conclusion. Why chemical strengthening of glass by ion exchange? Maybe not all of you are familiar with this type of process and technology. So ion exchange is a silicate glass processing approach with the capability to modify the mechanical, optical, and electrical properties of a formed silicate glass article. It consists in the interdiffusion controlled removal of ions located within the glass matrix. What is going to be removed, obviously, is not silicon, is not oxygen, but they are modifier, so namely sodium in this case. And this removal will be followed by their replacement with other ions coming from an external ion source, in this case alkali nitrate molten salts. When the incoming ions has a larger volume in respect to the removed one, and the process is performed below the transition temperature range, you will have uncompensated strains, which generate stress effect. And this results in an equibiaxial residual stress, which is characterized by a near surface compression balanced by an inner tensile status. This is the application of this type of process for mechanical application. The near surface compression layer works against the growth, the propagation, and the generation of surface flows, and this results in an effective increase of glass strength under bending. Chemical strengthening has the advantage to have practically no limitation in respect to the thickness, the shape of glass articles, and result in a superior optical quality. The industrial application of ion exchange for glass chemical strengthening can be dated back to the 60s, last century, and is presently widely used in a number of glass and glazing applications. I will show to you shortly which are the application in transportation and architectural. This is bullet-resistant glazing, where we use chemical strengthening. This is a marine application where you have large windows that are supposed to be loaded by significant load coming from the sea. And in this case, to reduce the cross-section and the weight and the thickness, we are using chemical strengthening. Aviation, as we already said, this is windscreen. Helicopters, military helicopters, or civilian helicopters, they have no glass, they have plastic material normally. But for military helicopters, you use glass as a windscreen. Architectural, this is the Apple stairs, where there are self-bearing elements chemically strengthened. And this is another architectural project in New York and the Hudson Yard fabrication building. Okay, and another interesting application is thin film and ultra-thin glass for consumer electronics and pharmaceutical applications. So you have foldable mobile phones and mobile displays that in this type of devices. And this is a very famous applications for pharmaceutical is an EpiPen, where the vials is made of glass, is a kind of borosilicate glass with a little bit of alkali inside, and it is chemically strengthened, and other pharmaceutical applications. Now, let's go into the theory of how it works. So this is a representation of the process, more or less. So you have the glass with the modifiers, which is, as in this case, alkali ions, sodium, which is in contact with the molten salt. In this case, is a potassium nitrate. Because it's molten, KNO3 is separated in K plus and NO3 minus. And then you have the exchange, which is driven by a gradient in the electrochemical potentials of the two ions, sodium and potassium, in the respective mediums. And then the molar volume of potassium is larger, and that's why you have strain at the surface, which is uncompensated because the process is done below the glass transition temperature, and this and the internal part create the constraints that generate the compression at the surface, balanced by a tensile zone in the inner one. So this is an equimolar chemical reaction characterized by the number of exchanged moles. This is how we can write down the chemical reaction. And if you multiply the numbers of moles that has been exchanged in the glass by the difference in the molecular weight of the two species, then you have a weight increase in the glass. We will use this equation later on. And this is more or less, again, a schematic representation of the stresses that is generated in this process. So you have a surface compression, SC. You have a dip of compression, which is the distance in between the surface of the glass to the point where the stress changes from compression to tensile, so when the stress is zero. And the other element is the central tension, which is obviously the remaining part of the central in the glass. So we have to discuss two elements, the thermodynamics and the kinetics of ion exchange. So the first assumption that we will make is that at the surface, this process can be divided in two parts. One is a surface process, which is in some way dominated by thermodynamics, and a bulk process, which is a kinetic process. And the surface is very important because if the time to reach the equilibrium at the surface is much lower than the total contact time of the glass to the salt, then you can treat that in terms of thermodynamics. You know, thermodynamics is a science of equilibrium, but this process is a non-equilibrium process by definition. So you have to take the assumption that the time to get equilibrium is much lower than the time otherwise you cannot use thermodynamics. And This allows you to define an equilibrium surface concentration. So this will be important because this will be, for the one that are normally using mathematical modeling of this process, a boundary conditions of constant surface concentration. But again, this is an assumption, this is an approximation that is true only under that condition. The other one, the kinetic transport process in the glass matrix. And this is characterized by another parameters, which is the interdiffusion coefficient, which is a kinetic element. So, based on that, we can calculate the ion flux through that equation. That is a Fick equation. Again, it's an approximation. And you can integrate, if you take the flux at the surface and you make the integration over the total time of contact, then you have the total flux that has been exchanged. That under that approximation is that equation. The interdiffusion coefficient that plays a role can be calculated from that equation, and is this one. So this allows you to define a function, a mathematical function representing the ion concentration in the glass. You see the red curve that you see there, and this is expressed in terms of a special function. Is a complementary error function. Is not a normal function, but this is a little, but can be calculated with most of the tools that you can find. And the other interesting thing is the average of that one. The average of the concentration is just the integral over the thickness of the concentration, and can be again expressed in terms of surface compression, thickness, interdiffusion coefficient, and total time. This is a simplified theory. It's very simplified, but it works for most of the application that we have seen. So the strengthening parameters, to the point we are interested to mechanical, and so the equibiaxial stress you see here can be expressed by that equation, and it's just the elastic modulus, the Poisson ratio. The difference, it is an analogy with thermal stresses, stress is a tensor, and the characteristic of this process is that it gives to you an equibiaxial stress into that direction. The arrow you see there is the direction of interdiffusion. And so you can have surface compression, central tension. Surface compression is just the value of that one when this is zero, when the coordinate is zero, and the depth of compression also. When you have the depth of compression, clearly when the stress is zero. So, and when is the stress is zero, and when the concentration is equal to the average. You see this equation here. This is zero when these two terms are equal. It's so simple. And so you can solve that equation for the case depth, and then you can come out with the value of the case depth. Now, having said what is the theory, with the simplified theory of ion exchange, let's go into the industrial production of potassium nitrate. You can do that in two ways: by chemical synthesis. So you start from potassium hydroxide with acid, nitric acid, and then you get the chemical reaction. And this is the industrial step that can. And also the other way, it's by mines extraction. So you take the salt from mining, and then there is an industrial process, and you can come out with two type of product: the crystallized nitrates and the pre-lead nitrates. Pre-lead nitrates is a spherical element of potassium nitrate with a chemical that keeps in a spherical shape. This is in general. This type of chemical I use for many applications. And this is a typical analysis of a potassium nitrate made by synthesis. It is very important. The purity of the salt is critical. And how we can evaluate your salt. If you make a chemical analysis like the other one, this is not sufficient, because in a chemical analysis, you find what you look for. There can be something there that you are not looking for. It can be important for the process. That's why what we do for a characterization is direct functional ion exchange test on small lab equipment. So this is the small lab equipment. These are the samples that we use. It's a clear float glass, low iron float, body tinted gray, and another specific glass that we use for process control. What we do with this, we determine the interdiffusion coefficient, the surface compression, and the depth of compression. You can use a weight gain technique using a balance like that, but be careful, not easy to do that. That means that you have to use an analytical balance, not a normal balance. And the characterization method, this is one possibility. The other one is by measuring the surface compression and the depth of compression. This is a differential surface refractometry that provides you this information. Is a non-contact method of measuring weight gain. So by weight gain, you have the D, the interdiffusion coefficient, and the case depth, while with the other one, you have surface compression and case depth. And this is a little bit a workout of the equation, how to get it. So you come with a weight increase, as you have seen before, and then after a few calculations, you come out with a determination of both interdiffusion coefficient and case depth. Okay, let's go ahead. Now we made a comparison of two types of salts. One is a salt that has been produced by, let's say, synthesis, chemical synthesis. And the other one was an industrial salt made by pellet mine extraction. And those are the values. Basically, the new pellet salt doesn't give to you any surface compression, any case depth, and also corrode the glass. That means that this salt is not suitable. Even if it's much cheaper than the other one, I don't recommend to use this, unless you have some methods to generate it, if it's possible. And it means not detectable. The other thing you can do with this measurement, if you do the schedule at different temperature, you can evaluate the interdiffusion coefficient. You see the column on the right, and it's a matter of fact that the diffusion coefficient depends on temperature from two parameters. One is the inactivation energy. This is a type of Arrhenius behavior. So this is put on a logarithmic scale how behaves the interdiffusion coefficient. And why this is important? This is important because if you have those data, then you can make prediction with other immersion times and with other temperatures of what can be the surface compression and the case depth. Conclusions. Chemical stainless glass by exchange is a silicate glass processing for industrial relevance. Is a user mainly in transportation, architectural glazing, consumer electronics, and pharma. Technological characteristics of ion exchange are surface compression and compression layer depth have been identified. The quality of alkali nitrate salt, namely potassium nitrate, is of paramount relevance for the process efficiency, and the methods to characterize and qualify potassium nitrate salt have been proposed. Results have been presented where potassium nitrate by chemical synthesis exhibits superior characteristics in comparison with mine-sourced and pellet potassium nitrate. And the characterization of a potassium nitrate salt in terms of D versus temperatures allows to build up a mathematical model to predict chemical strengthening parameters at different temperature and immersion times. Be careful of the point that I have in my model, I have not included any relaxation effect that are indeed of relevance, especially for surface compression. Not so many, more important for depth of compression, but are quite important for, especially for soda lime glass, for surface compression. I've finished. Thank you for your attention.